Morning, Rini.
Hello, teacher.
You not get up, is it?
No, I got up, but I was waiting for the link. Teacher only sent it 2 minutes ago.
How so long? Waiting for you?
No, I only just got the link 2 minutes ago.
Okay, let us make a start.
Yeah, okay. So, teacher, that means the whole Chinese New Year week teacher won't be around lah.
You got question to ask, you can ask, no problem. But teaching a bit harder lah. I'll be in Penang. Monday I'm free. You want to
Monday, you're what, sir?
Chinese New Year Eve, I'm alright.
Okay.
So the following Saturday or Sunday or probably Friday or Saturday, I won't be around. No? But if you want, you can ask question. I'll be in Penang.
Oh, but teacher won't be busy.
Say again.
Teacher
No,
won't
not
be
busy.
busy.
Just that you just text me.
Holiday.
I will give you a time when I'm free.
Okay, sure, teacher.
Hardly go out. Just go back to see my brother, that's all. Okay, chapter 9. Ideal gas equation.
PV equals to nRT.
You have no choice. As I said to you, your weakness is you want to study, but you don't want to do partial question. You don't want to try the problem. So that's why you don't know how to use the formula, because there's too many formula. Right? That's the problem. So you have to, after each topic, try the question. Make sure you know how to answer. That's your weakness.
No, teacher, here's the thing, teacher. Sem 1, they say chapter 9, 10, 11, they regularly ask every year. So these 3 chapter you master, they say it's good enough lah.
Don't trust that lah. Examiner won't just test two topic lah.
No. But every year it's these 3 chapters they'll keep asking frequently, either in section B or C. You know, teacher?
Yeah, but question 1 is always all the question, all the chapters. You cannot escape.
Yeah, I know, teacher, but most commonly I can't predict the other 8, but this one 9, 10, 11 always comes out a lot. That's what I'm trying to say lah, teacher.
Yeah, you can concentrate on that, but I think you should study all the other topic.
Yeah, just to be safe lah.
What your teacher say, I don't believe that lah. How to test you just a few topics?
No, I know, I get it, I understand.
In general, you have to test you all the topic. Then you have a fair. How to let you spot? You can't spot that. Okay, unless you can see the question paper, then you can be sure it is right or wrong. Just like you told me last semester, a lot of things not true. You told me last semester also, the teacher said this also not true. Because the last exam also, all the topics come out.
Yeah, all topic came out, but like I predicted, 9, 10, 11 came out both in section B and C this time, teacher.
Yeah, you can concentrate on that, but I think you should. It is very dangerous. You should try all the topics.
Risky lah, yes, but
okay. But you know all this. N is the number of mole, number of particles per unit volume. Sometimes it's symbol can be used for either of them. N number of molecules, Avogadro's number, and A. T is absolute temperature. P is pressure of gas. M is total mass. Small m is mass of particle. Mr is molar mass of gas. V is volume of container or volume occupied by the gas. R is molar gas constant. K is Boltzmann's constant or equals to R over Na. Okay, so all these formulas you need to know. Okay, don't bother about all these formulas, we'll derive that. C root mean square. Right, this
so
one.
Just give me 1 minute, sir.
Okay.
Okay, I'm back.
Okay, so you need to recognize the symbol. This stands for mean square speed. F is the number of degree of freedom.
Oh.
Right? And these are the topics that are covered in chapter 9. This is internal energy. This ideal gas equation is derived from kinetic theory. And that is for monoatomic gas, kinetic energy. So that is a syllabus.
Teacher,
Yeah.
one last thing, teacher. Yesterday, this Monday, right, teacher?
Yeah.
Monday, Tuesday, there's like the normal test lah they give for SEM 3 is not the important one, but still like I'm not studying because I want to focus on the SEM 1 first, can right?
So next week you don't need to, you still got school lah.
Yeah, next week still got school. Monday, Tuesday won't learn anything because got exam. Not the important kind of exam, not the real exam yet, just like a trial thing.
Or trial exam lah. So close, I'll give you a trial exam.
Yeah, actually not to say trial lah, but it's just like a normal pentaksiran lah. But usually,
Okay.
but now I want to focus SEM 1 first lah, because more important.
Yeah, you better concentrate on SEM 1 because the exam is very close after Chinese New
Because
Year.
later, after that, SEM 2, SEM 3 can focus lah, one shot.
After Chinese New Year is your exam already, which is very fast.
No. After Chinese New Year, one more week after that, only exam.
Yeah. So when is your school holiday for you to
Oh,
study?
no, my exam February 14, right? Physics,
Yeah.
correct? So 14, 15, 16, 17 exam. After that, on 28 is a holiday. 26 Saturday, but 28 lah, it's starting.
Oh, before that, don't know holiday lah.
Before that 1 week don't have holiday lah, normal school. After that 1 week of exam, normal school. Then only
study like that?
holiday.
How to study? No time to study. Okay, let's carry
No,
on.
no, the holiday, February 28 until March 20, 3 weeks of holiday.
After that is your another paper already, second term exam.
No, second term exam is after the semester 3 finish.
Oh, like that lah.
Like that. All in May.
Okay.
So the holiday I got 3 weeks can study lah.
Okay.
Yeah.
Okay, know where to find your constant, Avogadro's constant from your value of constant given in your exam paper. Boltzmann constant, that is for this part. Molar gas constant. Okay, the other part, I don't think you will need that. Ideal gas. Yeah, real gas have complex behavior, but it's possible to make progress in understanding gases by developing a simplified model of gas called ideal gas. So even though real gas is complex behavior, we can try to narrow it down to a simple model to help us understand. Right? We call that ideal gas. A link between behavior of gas molecules and temperature can be established. Right? So we can do experiment to find the link between gas molecules, behavior of gas molecules, like the mass, the velocity, and how it's related to temperature. This provides introduction to a concept of thermodynamic temperature. Right? So give you an idea how we measure our thermodynamic temperature. The ideal gas equation, make sure you know how to define 1 mole is the amount of substance which contain many elementary units. You can replace elementary unit as particle as there are atoms in 12 grams of carbon 12. Okay, that means 2 grams of hydrogen gas, 32 grams of oxygen gas. Right? Entities can mean atoms, molecules, ions, electrons. So all these definitions should be in your head. Avogadro's constant, right? Na is the number of atoms in 12 grams of carbon 12. Right? And that's the value. Right? That value is given in your where is the value? There, right? It's given. So you can check, no need to memorize it, know where to find it. Right? Molar mass MR is defined the mass of a mole of the substance. You can unit usually will be gram per mole. You can change to kilogram if you want to. So if carbon 12 will be 12 gram per mole. So if you have m kilogram of substance or molar mass MR, the number of mole is just n equals to m divided by MR. Okay, it's just a repeat, that's all. So that is very simple. All these things you need to know. 1 mole, Avogadro's constant, and then different way of calculating a mole, either from number divided by Avogadro's number, or from mass of the substance divided by molar mass of the substance. Okay? We won't bother about all these experiments. Usually gas law, what you study, we have to look at 2 variables, either pressure changes with volume, temperature and mass are fixed, or pressure with temperature, how the pressure changes with temperature, we keep the volume and mass constant, or variation of volume with temperature. We have the experiment, you can only investigate 2 variables or 2 parameters at the same time. The others, we have to make sure it's constant. So here, volume and temperature, we keep constant pressure and fixed mass.
One of it has to be constant.
No, 2 of them are variable. The others are constant.
Yes, yes. The last one constant, the other 2 variable.
2 variable only. The others are constant.
Yeah.
So these are the parameters. Volume of container or volume of gas in the container, pressure of gas in container, absolute temperature, and number of molecules of gas, m mass of gas molecule. That formula I have to remember, ideal gas equation. So n times m is your total mass of gas.
Oh.
Can you, instead of molecule, you can use particle. The volume, pressure, and temperature, we call that macroscopic property because these are things that we can feel or we can measure. We won't bother about all these STPM work. We just need to know, just need to know Boyle's law, roughly. PV equals constant, and know how the pressure and volume changes, the hyperbolic graph, and V1 equals V2 V2. If you use a higher temperature, then the curve is a higher curve, that's all. And each of the curve we call isothermal. Stop me if I'm going too fast. Since I'm just reviewing you, no point in going too slow.
Let's just go back to the one slide. I just want to read it. Give me 30 seconds. Yeah, that means the temperature here is a constant. That's why T2 more than T1. That means the one graph above, that means it's higher, right?
Higher temperature, that's all. You need to recognize that.
Okay. T1. Oh, memorize the formula also. Yeah. Okay.
Pressure law. Pressure of fixed mass of gas at constant volume is proportional to absolute temperature. Or P over T is constant. And this is the apparatus. I don't think we need to bother about all that. This is your STPM work. We won't test you on that. Then you need to recognize the graph. And we use pressure 1 over theta. Pressure 1 at temperature T1 equals to pressure 2 over temperature T2. That's all. You need to recognize that. And then you need to recognize if I plot it in terms of Celsius degree, that's what I can reproduce a graph backwards to minus 273.15. Right? Where we call this one our absolute temperature. So if I plot it at that absolute temperature, then it's a straight line passing through your origin. Right? And then you need
Okay,
to
so if you plus 273,
pass to 273.15.
yeah.
That is the absolute zero temperature.
Hmm.
Okay.
Okay.
Then Charles' law. As I said, don't need to worry about the experiment. This is just to review with you. Right? Volume is proportional to absolute temperature. And then there's a constant there.
No, no need to worry. So the
Experiment, they
experimenting.
won't ask you. They just
Oh,
they just want you to roughly know what you studied at SPM. So you use temperature T1 and volume V1, temperature T2 and volume V2, and then your pressure and the mass is constant. Then you will get V1 over T1 equals to V2 over T2. If you draw the graph, volume over temperature, right, you get a straight line graph. Remember, all these experiments you done at room temperature and atmospheric pressure. Right? We didn't investigate higher temperature or lower temperature. Right? But we just do at room temperature, that's all, to just show roughly, So if we produce a line backwards, you get minus 273.273 degree 0.15 if you want to, degrees Celsius, or you plot the volume against absolute temperature that pass through origin. You just need to recognize all this graph as well.
okay.
Then
PV
combining
equals to NR.
these three experimental equations, right, you get PV over T is constant. Okay.
NR is constant, right?
So now we want to find the constant. So 1 mole of gas at 1 mole of gas, right? We use 1 mole of gas. The constant is known as molar gas constant. Right? So R equals to P. And we are just using this equation. We call the constant R. And then we just subtract your R, take the T down to get this equation. So PV is in joule, right? It's work done. And then this is Kelvin. And remember, we use 1 mole, not 1 mole. So the unit is joule per kilogram. Sorry, joule per Kelvin per mole. Okay, so we use 1 mole, then R is called the molar gas constant. This is a formula you need to memorize. Now, how to calculate the value of R? We use standard temperature and pressure. Right? There's a standard pressure. There's a standard temperature, 273.15 Kelvin. Right? With 0 Celsius. And that's your volume, 0.0224 per cube. And we use the equation to calculate your R. That's how we get our value R, joule per Kelvin per mole. And for N mole, we just multiply by N, that's all. Okay, so this is the formula you need to memorize. Any questions so far?
So that means the PTV value is the one constant values, is it?
PV equals NRT, that's all. So
No, the P, the 1.01,
temperature
270.
constant, number of mole constant, then PV equals to constant is your Boyle's law. So if you keep the volume constant, N constant, then your P against P is proportional to P is your pressure law.
Oh yeah.
Keep your pressure constant, you keep the number of mole constant or the mass constant, then your volume is proportional to absolute temperature. That's all.
So P over T equals to constant lah.
Yeah, you should be able to play with the formula to get your different law.
Okay. PV equals to okay. No, just so PV equals to RT when there's no mole dimension, only you use mole when dimension only lah.
Just play with the formula
Or
only to get what you want. As I say, you only need two variables. The others are kept constant.
constant, okay.
Right? There's another formula you need to remember. Ideal gas equation. PV equals to NKT. Right? K is called Boltzmann's constant. And it's R divided by NA. Right? That's Avogadro's number. And then we can do it to calculate the value. Right? As I say, the value is given in your data sheet. Right? Know where to find it. Okay, there's your value for K and Avogadro's number are quite close together. Right? It's called K or KB, joule per Kelvin. Okay. Okay, so there's a value of K. How to derive this formula? Right? N stands for number of molecules. Right? The N or number of particles. I call it data sheet lah, other than physical constant. Derivation, right? From PV equals to nRT. Replace your N. Right? That one with number of particles divided by Avogadro's number. And your R over NA is your K. That one is your N. And R divided by NA is your K. That's how we get our value. Right? You either memorize it or you derive it. You cannot memorize it, derive it. Doesn't take a lot of time. As long as you remember this formula. And remember N, small n is N over NA. Okay. So these are the two formulas you need to memorize. As I said, the only way to memorize is to do the question, then you force it in.
First will be hard, then later will be okay lah.
As soon as you try the question, just like I teach you, I have to try all the question. A lot of things are new to me. I have to try the question, then I understand. That's how I can teach you. So far, I can see I have not much problem because I've gone through the question. Problem that I have got stuck, I learned to understand. Right? When I was your age, I couldn't do some of the things there, but now I can do it because I tried the question and solve it. That's how you progress. Okay. So these are the things.
Okay.
It's called equation of state or ideal gas equation. Either one of them. And there's your number of mole. And K is your Boltzmann constant. Any question?
So K equals to R over NA is Boltzmann constant lah.
Okay.
Yeah, so far no questions. All like normal constants thing only. Yeah.
Right. So of course you have to define what is an ideal gas. As long as you obey gas law, obey the ideal gas equation at all temperature, pressure, and volume. Then that's called ideal gas. Point mass with no attractive force.
What does point mass with no attractive force mean, John?
Point mass means the mass is very small compared to the container, compared to the volume of the container, which you define.
So you try and tell me even if the container is big but less point mass, so no attractive force lah.
When we say point mass, we are looking at we will define later on. We are considering that the volume of the masses compared to the volume of container very small. So that it looks like a point compared to container.
Less attractive force.
So in normal cases, it should be satisfied. But not attractive force. Not attractive force only for ideal gas. Only for certain
Ideal gas.
condition, which will define the condition under assumption. Okay, so that's
Ideal
how
gas
we,
means is assumption, right? So it's not a real gas, but right?
as long as the real gas follow the assumption, then it's ideal gas. But as long as it doesn't follow the assumption, then it's normal or ideal gas anymore. That's why we expect to change in behavior.
Oh, so the normal gas has to follow all these three conditions, then only become an ideal
So
gas lah.
for where it doesn't satisfy the condition for ideal gas, then it's no more ideal gas anymore. It's real gas.
Oh, okay.
So like when we do experiment, room temperature and atmospheric pressure, we find that you obey the gas law, you obey ideal gas equation. We can try all the temp. Of course, it's not true all temperature, pressure, and volume. Right? We only have certain temperature and certain pressure and certain volume. And then at room temperature, okay, we will find that the particles are very far away from each other. So if they are very far from each other, there's no attractive forces. Okay.
Okay.
Right? So many gases at room temperature and moderate pressure behave ideal gas. Right? As long as you don't go to very extreme temperature or very low temperature or very high pressure, then you will be okay. So ideal gas behavior based on experimental observation of gases such as air, helium, nitrogen at temperature, pressure around room temperature and atmospheric pressure. So as long as the original experiment was done with air, helium, and nitrogen at room temperature and atmospheric pressure, then we are okay. It behaves like ideal gas.
Oh, it must be air, helium, or nitrogen lah.
And it can be other gases also, but I have to be careful about the temperature.
Temperature and pressure lah.
Right? So this equation of state, just to summarize for you, what does system mean?
Practically ideal gas means is basically like a perfect gas, but then it's like just trying to every gas is
ideal
trying
gas
to
is in
fulfill
our
the
head
condition,
only.
right?
That so real gas can be made into ideal gas as long as we provide certain condition is obeyed.
Those three conditions lah.
So it doesn't obey ideal gas equation for all temperature, pressure, and volume. Which your syllabus remove already. There is an equation for real gases which you don't need to study. Right? You need to know what does each of the terms stand for, how to calculate the absolute temperature, no need for 273.15. Okay, 273 good enough. So these two formulas you need to remember. N is the number of molecules or number of particles. K is Boltzmann's constant. Is molar gas constant divided by Avogadro's number. Real gas behave as ideal gas. Right? Pressure must be sufficiently low, about 1 atmosphere or less. Temperature must be sufficiently high, about 300 Kelvin or more. Right? Not too high, not too low. Okay. So if it's ideal gas, we just draw our PV graph.
Back again, sorry.
Say again.
No, last slide, again, please. Pressure must be very low, about 1 atm or less. Temperature must be high. Okay.
That means it's about room temperature. Room atmospheric pressure. About atmospheric pressure. And about room temperature, yeah, okay. Not too low temperature, because remember, at too low temperature, it may become a liquid. And then lower temperature becomes solid, so it's no more a gas anymore. So as long as it's away from the boiling point, yeah, it's okay. Right? We can draw graph, PV graph, PV against pressure. Right? If it's ideal gas, it's a constant, you should get a straight line. right? And then we can draw it for different gases. You can see that it doesn't obey. It's not ideal gas anymore.
Yeah, which is not ideal
The curve
gas.
is no more horizontal line.
Yeah. So what about the hydrogen and the helium, teacher? They almost behave like ideal gas, but they are not curved.
Still sloping. It's still sloping. So we want to make real gas the ideal gas. We have to use about room temperature, right? And about 1 atmosphere. Right? You can try that with right, PV graph of methane. We can see that right, only about 200 degrees Celsius means quite a high temperature already, about nearly more than 500 degrees, and only at low pressure. Atmospheric pressure there, it will obey. After that, it doesn't obey anymore. Temperature too low, so it doesn't obey anymore. Okay.
Too high, it obey a bit, but then not everything.
So
It's
the
only that
PV graph
little
for different gases we can plot, and then we can study how it behaves as ideal gas. Right? Methane only at this pressure.
But usually it's a straight line lah.
As long as it's a horizontal line, it's okay. That is for your info. Ideal gas behavior and relationship between PV and T are based on experimental observation, such as air, helium, and nitrogen. So we do the experiment for air, helium, and nitrogen at room temperature and atmospheric pressure, and it works, and the real gas becomes ideal gas. But of course, in real life, if we change to more extreme condition, low temperature, the molecules are quite close to each other. So we can expect that there is intermolecular force already. So it's no more ideal gas anymore. Or when we use high pressure, we squeeze all the volume to very small. High pressure, the molecules are also very close to each other. So we can expect it doesn't work anymore. Right? So there are conditions we have to ensure that the real gas obey, then it will behave as ideal gas.
So that means if it's low, the very low temperature one also not helpful. The very high pressure one also, it won't be ideal gas.
Because you have intermolecular force coming in, when the particles become too close to each other at low temperature or high pressure, then there is going to be significant intermolecular force anymore. But if they are far away from each other, intermolecular force, you can think of it as almost zero.
Okay.
Okay.
No, just 1 minute. So intermolecular forces means like you'll come and then
Attraction and repulsion between particles.
Oh, that means it repulse and then it also.
If it's too near, it will attract each other. If you press it too close, it will repel each other. That's all.
Yeah, moving very fast lah.
Not moving very fast. Yeah, particles are coming close to each other. That's intermolecular force, attractive force or repulsive force.
Oh, it can be either one lah. It's either attractive or repulsive.
Far away, it's attract each other. When you push it too close, then it repel each other.
If you push it too far, then it become repulsive.
If it's too far, if it's close together, it becomes attractive force.
Attractive.
Right? If it's very, very far away, then there's no negligible intermolecular force.
Okay.
Right? We can look at nitrogen, try how the volume changes with temperature. Then we can see that it's a straight line. Right? As long 77 Kelvin, that's become a liquid already. That's 77. So as long as it's far away from the boiling point, it's quite okay. It behaves as an ideal gas. You can see the straight line there. But as soon as it's near the boiling point, it becomes a curve already. That's what it means by this part is normal. This part is real gas already. This part is ideal gas. Okay.
1 minute, nitrogen
It's
is
just for
cooled
info
down
only.
once.
Just to show you real life situation.
Yeah, that means it won't follow lah. That
You
means
won't follow
at the
you won't pass through origin anymore. But as long as its temperature is high, it's okay. Right?
temperature high, okay, but yeah.
Near the boiling point is 77. Then it go away from ideal gas behavior already.
Yeah, lah, low temperature what cannot. High pressure also cannot. So yeah.
Okay.
With kinetic energy molecules are low, okay, and the attractive force becomes significant. Oh, so you try to tell me if we did obey ideal gas means
I'm trying
there
to
wouldn't
tell
be
you
attractive force.
that any gas will obey ideal gas equation as long as you have certain condition they follow, which we will go into that when we go to kinetic theory. So don't spend too much time on that. Right? To help you understand the kinetic theory, why we have to set certain assumption or certain condition before it become an ideal gas.
Okay.
Okay.
Okay, can have this 30-minute class and then 5-minute break, Can
You have to finish the hour. You got 2 hours.
Yeah, I got. But usually when you give me 5-minute break, then you extend. Yeah, but half an hour usually that's. You don't want me to get tired, what?
That's why I'm giving you. Just now you told me already. Now it's almost 1 hour. Let it go for 1 hour.
Okay, sure.
Okay, so we won't worry about this. These are just extra information. How scientists during the early days, during the 19th century, they will go to all extreme cases to increase the pressure and then study where the
Nothing, you don't need to know lah.
this one is just for your info in case you want to study. Okay, so this one summarizes for you the formulas that you need to remember. Don't worry about the worksheet there.
9.2. Oh, this is 9.1.
All that. You're spending too long time here.
Yeah, change.
Okay, now we are going to pressure our gas. We're going to derive this equation.
I can't see your slide, it's
sorry. Forgotten to share screen. Can see now?
Yeah, now can see it's moving. Okay.
Okay, so we are now going to.
Yeah, got chapter 10. Some also have to go very fast, I guess.
Derive this equation. And at the end of 1 hour, we give you a short break since you are going to have 2 hours. Okay, we are going to pressure of gas. Your book is 216.
Yep.
As I say, all this
the 6 rules lah.
Your book use that lah. For 1 mole is just a VM. Okay, so we are going to cover 9.2. We're going to assumptions of kinetic theory of ideal gas. Derive and use the equation for pressure exerted by ideal gas. We're going to derive this equation. Then we are going to cover molecular kinetic theory. State and use the relationship between Boltzmann and molar gas constant. We have done that already more or less. Okay, so that's your STPM work. We won't spend too much time. Just to show you, we need to define another term pressure. Okay, so we cannot have just force. We have a bigger area. Then the force on the pressure on the ice is going to be less, so it won't sink into the ice as well. So we define
If
pressure.
the pressure below is low, that's why you don't sink into the ice. Is it?
Yeah, the pressure, when you wear a ski, then the pressure is higher. Sorry, the pressure is low, so it won't sink into the ice.
Oh, because it's very light, is it?
You
That's
spread
why
the
low pressure.
force over a bigger area. That's all. That's why it is very silly for a woman to wear high heel shoe and go and walk in the beach. She will struggle walking there because the
surface area is big.
the small area will cause what you call that, cause it to sink, and then she will have problem walking. Okay, so
like the normal sport shoe, that's why it's okay lah.
So that is our definition for normal force over surface area.
FOA.
Okay, so we won't spend too much time. It's just a review.
Yeah.
We can come out
Equals to
to
FOA.
find the unit or dimension. Force is in Newton. Area is
NM -2.
So we can, this is Newton, kilogram meter, S minus 2, cancel the meter there. We can either write as Newton meter minus 2 or call it Pascal, or we can write as kilogram meter minus 1, S minus 2. Right? That is your topic 1.
ML -1, T -2. That's the other one lah, derive.
You use dimension. That is a scalar quantity.
No direction.
Okay. So, ideal gas equation, we use macroscopic properties like pressure, volume, and temperature, how they are related to each other. Then you give a good description. But of course, as scientists, we are interested more. How? Why do they behave this way? Why is PV equals nRT? Right? So
PV, ideal gas equation.
So we now want to see how it's related to, try to understand it as like using Newton's law on the particles in the room or particles in the box there. Right? It has velocity. How does the kinetic energy relate to temperature and all that, and volume? So that comes to kinetic theory. Right? Kinetic theory of gases is a theory which links macroscopic property, the mass, the velocity, kinetic energy of particles to macroscopic property. So you want to relate mass, velocity, and kinetic energy with volume, pressure, and temperature. Right? We have to make certain assumptions that ensure that real gas, if it's going to be ideal gas, then it must follow this assumption. Right? We are going to use Newton's mechanics that we have studied earlier, right, to apply to the gas particles. Right? Remember, the gas particle move with a range of velocity. And review, all matter is made of particles. Particles can be atoms, molecules, or ions. Okay? That's the size, 10 to the power minus 10 meter. Particles are in continuous motion. And that's the Brownian motion. Right? Don't need to worry too much. This is your STPM work. It's just to do the experiment in a dark room. Right? We can smoke there, and then we can shine light. We can observe using a microscope to see the irregular motion of the particle. So that shows us that in this case, the air particle is knocking on the smooth particle. So that's why become the conclusion that the air molecules are moving. Okay, so I won't bother about all this. This is STPM work. It won't come out, it won't test you. Okay, so basically, Brownian motion experiment shows the continuous random motion of particles of the gas or liquid. I can think of.
So can you go back 2-3 slides, Archer? Sorry.
Why you want to waste time on all this for what? All these are SPM work, it won't be tested.
So you just want to see only.
I just want to review with you, that's all. Just to.
Okay, understand. Okay, can continue, Rajan.
No point in reviewing all that. When I first teach you, I just want to review with you. Now you want to go very fast. You don't have time.
Yeah, okay. Okay.
Okay, so now assumption is just tell how does ideal gas behave. As long as you
Yes.
follow this assumption, then it will behave as ideal gas. Right? This one is to help you. Pint, P-I-N-E-D, P,
Okay.
point mass, point molecules. That means we compare the volume of the molecules, all these tiny molecules, we squeeze it up, it has a volume. Right? The volume is very small compared to the volume of container. So normal, in a room there, no problem. The gas will behave as ideal gas because they are far apart. The idea is they are far apart. That's why it's called point molecules.
That's why it's smaller lah.
And I for intermolecular forces. Right? The molecules are far apart, their intermolecular forces are negligible.
Oh yeah, like you
As long
said,
as they
like
are far apart,
intermolecular means they attract.
there is no forces between them. The forces is negligible. But when you squeeze it to where they become too close to each other, then the intermolecular force, attractive force will be there already. There is no more ideal gas anymore. You have to keep that in mind. Right? The third one, N is number. Right? We are going to use statistic. So the number of particles or number of molecules must be very large, even in a small volume. And that large number of collision occur in a short time. The average of the many impacts give a smooth pressure. Particles are in continuous motion. Okay, that's your N. E, elastic collision. Molecules are perfectly elastic sphere that they undergo elastic condition, elastic collision. In collision, one gives kinetic energy to another. No energy is changed or the form. That's what it means by elastic collision. Right? That's why the molecules all have different kinetic energy or different speed, because some gain kinetic energy, some lose kinetic energy. Duration. The duration T1 of the molecule of the collision is negligible compared with the collision between molecule. Right? In this case, when we think about collision between molecule, right, the duration is where it just hit the wall there. That's the time, T1. T2 is between the molecule, the collision between molecule, but usually we are thinking of it hits this wall and then it comes back and hits this wall. That's all. So as long as T2 is very much greater than T1, we are all right. That means the molecule doesn't stick to the wall. Okay, so T1 is the time of collision with the wall, that we call duration. And T2 is the time to hit the wall and return to the wall again. At one side of the wall. And we're not interested in collision between molecules or particles, because there's no way we can take into account for this. We are more interested in hitting the wall, the collision between the particle and the wall. Okay? There's no way to measure the time of collision between molecules. That's why we have to use approximation. Right? Because the pressure is due to collision of molecule with the wall, not between molecules. Right? The pressure of the gas is due to the collision of the molecules with the wall. Okay, so we are going to derive this formula. Know what each symbol stands. Capital N is the number of particles in a container. Small m is the mass of particle. C is the speed of particle. And then that symbol there, the whole symbol there, call it your mean square speed. This whole symbol stands for mean square speed. P is the volume of container. And P is the pressure. Okay, so basically, the first thing is kinetic theory states that the molecule of gas move continuously at random and often collide with the wall container. When the molecule collide with the wall container, it undergoes change of momentum.
MV minus MU.
Right? We're going to derive this equation. Rate of change in momentum is the force acting on the molecule. And then we can use Newton's third law to find the force acting on the wall, which is just opposite, equal and opposite. There's Newton's law. Or this one, which we are going to use. Pressure is the average force per unit area. Right? The total force divided by the area. Right? Total force divided by area. This is for one molecule. Okay, let's start the derivation of this formula. Right? We consider a cube of side L. Right? Consider a cubic container of length L containing n particles. We assume it's monoatomic and each of mass m. Right? We make assumption all the particles move in the x direction. That's why we call it ux. Right? Same speed. Particles are monoatomic. Right? One atom only. Right? Remember, we are interested in particles colliding with the wall container. We are not interested in collision between particles.
Oh,
That one we cannot see, we cannot measure also. So only on the
we
wall,
won't know also.
we won't know. But it's a good approximation. That's all we are interested in. Give us some idea. Imperfect, we can modify later on if you want to. Right? T is the time to hit the same side of the wall. That means we are going to have one side, this side. It starts from here, it goes to this wall and it come back. That is your time T. Distance travel is just your, it travel from one wall and come back. Distance is 2L divided by your total distance is 2L. Speed is distance divided by time. Right? So that's our ux. Distance is 2L. Time is your T. Okay, let's look at the particle of mass M with speed u. And then after collision is elastic, so it's minus u. Right? That's the wall of container. That's the wall of container. Right? It's a vector quantity, so we put a negative sign there. So for one molecule or one particle, the momentum, initial momentum is P equals mu. Change in momentum, right? Remember,
MV minus
momentum
MU.
is also the same, but I got a negative sign. The change in momentum is mv minus u minus 2mu. Distance for particle to impact the same face of the wall is 2L. So we can calculate the time, 2L divided by,
Newton's third law lah.
I haven't applied the third law yet.
Oh, okay.
I'm just trying to derive it, right? Derive the force. Right? So here you are just using distance divided by speed to calculate the time. So force on the particle, right? Newton's law is just to calculate the force on a particle. Right? There's a change in momentum over time. So change in momentum is this one, minus 2mu. Right? Time, we take this one, divide here. 2 and 2 we can cancel off. And then we can multiply by u bottom. Multiply by u, the top there, or numerator. Right? We didn't do anything illegal. U and u cancel off. Then we get our mu squared. And then there's a L left. There's a L left. Okay, so far?
Yeah, you take the change P and over T, then you just substitute the value and then you times U. So why you times U?
I want to get rid of the u here.
Oh, okay. Yeah, still makes sense. Yeah, 2 divided 2, 1, and then mu square over L lah, yeah.
Okay, so there is a force on a particle all moving in one direction. Right? Now we want to calculate the pressure on this side. Right? Remember, it's moving in the x direction. We want to calculate the pressure on this side there. Right? Remember, that's our assumption. All molecules have the same velocity. All particles move in the x direction. Force on the wall by n particles. Then we just multiply by n, that's all. Right? Force on a particle times n is the total force on n particles. So it's for the wall. Then we just put a negative. Right? That's the Newton's third law of motion. Negative of the force on the particle. So pressure is the total force divided by the area that is hit on the wall. Right? And molecules hit on the wall. So our total force is that. Substitute for Ft here. Right? Our area, that's your L is there. That's your L. AL is your volume. Okay, so that's our formula. Okay with that so far? Anything not clear?
Over L and then over. Oh yeah, okay. B equals to. Oh, this is all what you call that derivation lah.
Okay, so now we want to get rid of these two assumptions. We find this is not true, right? These two assumptions is not true. So we want to modify our formula. This formula is only for all that. Right? So we'll do correction. This is what we have derived, the average pressure. Correction for assumptions. And we can expect, because the pressure on the wall is the same, so we can expect that 1/3 will move to the x direction, one third will move in the y direction, 1/3 will move in the z direction. Right? So we can divide this by, right? Take a v across there, so it's 1/3 there, that's our 1/3. Then, in general, molecules can have any speed, not just a particular speed, and can move in any direction, any of the three directions. So we replace the u with our c. Okay? Or usually textbook will use this one now. Right? This is for x direction. Then we have to correct it for x, y direction. There's a y direction. There's a z direction. Right? So the speed can be any value. Right? This is speed in x direction, speed in y direction, speed in z direction. Then the speed can be in any direction. So we replace your c square equals u square plus v square plus w square. So we get that. Right? And the speed can be any value. That's why we replace it with that. Okay.
Same. Oh, that's the value lah. Okay. Different speed means root means square speed lah. Okay. Oh, different only root means square. Same only means c square. Right.
This one, all the speed are the same.
Yes, yes.
This one is the speed at any time can be any value. This one, all
that's
the
why
speed
root means square lah.
All the speed are the same. One speed only in the x direction, in the y direction, in the z direction. But we don't want that. We want any speed. Okay, so that is our equation. Or you can memorize this formula. This is your density. Okay, so I think maybe it's time to stop for a break. 5 minutes break for you to refresh yourself. Let me just see anything else I need to. Okay, this sometimes it can come out in this form. This one I just replace N divided by V as that N as well. So I get this
Yep.
equation. Okay, so these are, you can memorize this formula, whichever you prefer. I recognize there can be other formulas. Okay, so all these tell you that the pressure depends on number of molecules. More particles, more pressure. Greater mass, it hits the wall, greater pressure. Greater volume, it has to travel longer distance, so the pressure will be smaller. Greater speed, greater pressure. Okay?
Greater volume, pressure be lower, right?
It has to travel longer distance before it hits the wall. So of course the pressure
Yeah,
is
that's why it's
smaller.
lower lah.
Okay, so I stop here. Give you time to take a break and refresh yourself before we carry on.
Okay.